Saturn's iconic rings vanish into a mere speck of light. Our solar system's grandest spectacle is utterly dwarfed by a single alien world. This is J1407b, an exoplanet whose rings are not just bigger, but 200 times larger than the entire ring system of Saturn. By the end of this journey, you will understand how this impossible structure challenges everything we know about how planets form. We are looking at a cosmic mystery where gaps in starlight hint at hidden moons larger than Mars, and where a single year lasts over a decade. What does a place that defies all our expectations make you wonder about the universe? The story of this ringed behemoth begins not with a telescope image, but with a flicker. Back in 2012, astronomers working with the SuperWASP project, a network of robotic cameras scanning for planets, noticed something profoundly strange. They were observing a young, sun-like star called J1407, located roughly 434 light-years away in the constellation of Centaurus. Normally, when a planet transits or passes in front of its star, it causes a brief symmetrical dip in the star's brightness, but the data from J1407 told a different story entirely. The light from this star didn't just dip, it plunged in a series of jagged, chaotic drops and rises that lasted for weeks. This wasn't the signature of a simple, solid planet blocking the light. This was the fingerprint of something vast, intricate, and structured. It was the shadow of a ring system so enormous and complex that it sculpted the starlight into a wild, undulating pattern. From that single, bizarre light curve, the planet J1407b was inferred. We have never seen it directly, we have only read its shadow, and what that shadow reveals is staggering. J1407b is almost certainly a gas giant, a vast world of swirling hydrogen and helium, but pinning down its exact nature is tricky. Based on its gravitational influence, estimates of its mass range wildly from perhaps 10 times the mass of Jupiter all the way up to 40 times. That upper limit brushes against the realm of brown dwarfs, failed stars that never ignited, so we are left with a fundamental question at the very heart of this mystery. Is J1407b a planet with rings of unbelievable scale, or is it something else entirely, a substellar object wearing a disk of debris that we simply call rings? The shadow hints at an answer, but the true identity of this distant titan remains tantalizingly out of focus. That shadow told a story of impossible size. To truly grasp it, we need to step back and look at our own solar system's champion. Saturn's rings are magnificent, a delicate halo of ice and rock stretching 280,000 kilometers from end to end. That distance is so vast it could neatly contain over 20 Earths placed side by side. It is the defining feature of our cosmic neighborhood. Yet, when placed beside J1407b, Saturn's entire ring system shrinks to the size of a tiny, gleaming coin held up against the side of a house. The rings of this distant world are estimated to be nearly 120 million kilometers in diameter. Think about that number, 120 million kilometers. That is roughly the distance from our Sun all the way to the orbit of Venus. If you could somehow place this ring system around our own Sun, its outer edge would sweep through the inner solar system, brushing past Mercury and nearly reaching our second planet. The scale is not just large, it is categorically different. A helpful analogy makes it brutally clear. If the entire, glorious ring system of Saturn were the size of a frisbee you could toss in a park, then the rings of J1407b would not be a larger disk. They would be a full American football field, complete with both end zones. That is the leap in scale we are confronting. This is not a slightly bigger version of what we know. This is an architecture of such staggering proportions that it forces us to question the very rules. How does a ring system that enormous even hold itself together? What kind of gravitational anchor is required to maintain something that spans interstellar distances? The sheer physical reality of J1407b's rings pushes against the limits of our models, suggesting we are looking at a celestial phenomenon in its most extreme and perhaps fleeting form. Such a monumental structure could not be built from ice alone. Saturn's brilliant white rings shine because they are made of pristine water ice, reflecting sunlight with dazzling efficiency. The rings of J1407b, however, tell a darker story. The intricate pattern of shadows they cast upon their star suggests a composition far more complex and murky. These rings are likely filled with vast amounts of fine, dark dust and rocky debris, materials that absorb light rather than reflect it. Think of the difference between freshly fallen snow and a gravel road at dusk. One gleams, the other swallows the light. This composition is our first major clue that we are not looking at a permanent, stable ring system like Saturn's. Instead, we may be witnessing something much more primal, a circumplanetary disk. This is a term astronomers use for a swirling pancake of gas, dust, and rock that orbits a young planet. It is the very cradle of moons. In our own solar system's ancient past, Jupiter and Saturn likely had similar disks from which their families of moons coalesced. What we call the rings of J1407b, then, might actually be a snapshot of a moon factory in overdrive, a disk of raw planetary construction material on a scale we can scarcely comprehend. Within that vast dark disk there are hints of intricate structure. The long, complex dimming of the star was not smooth. It contained multiple sharp dips and plateaus, signaling that the disk is not uniform. It has dense bands of material and, crucially, gaps, and gaps are where the story gets truly compelling. In Saturn's rings, clear gaps are carved out by the gravitational influence of small shepherd moons. At J1407b's scale, a gap in the disk would require a shepherd of immense power. Analysis of the starlight data suggests one particular gap is so wide and clean that it points to the presence of an unseen, forming moon within it. This potential satellite, if it exists, could already be a world larger than Mars, clearing its orbit within the primordial chaos, so we are left with a breathtaking possibility. We may not be seeing a planet with rings at all, but a planet with a full-blown solar system in miniature under construction around it, where future moons are being sculpted from the dark dust before our very eyes. This intricate pattern of light and shadow is our only map to this distant system. The long, jagged dimming of the star J1407 was not a single event but a series of them, like a complex musical chord played out over 56 days. Within that data, astronomers identified at least one major, clean break in the signal, a sustained period where the starlight grew noticeably stronger before dipping again. In the language of rings, a gap like this is a gravitational signature. It is the celestial equivalent of a freshly plowed lane in a field of snow, a path cleared by something with considerable pull. Around Saturn, the tiny moon Pan orbits within the Inca gap, its gravity sweeping the region clear of ice particles, maintaining that dark line. At the scale of J1407b, the forces required are monumental. The most prominent gap observed in its disk is staggering, stretching over tens of millions of kilometers. To create and maintain such a vast, empty corridor, the object responsible must possess immense gravity. Calculations suggest this unseen shepherd could be a proto-moon, a world still gathering mass from the surrounding disk that has already grown to the size of Mars or even Earth. Let that sink in for a moment. We are potentially looking at the birth of a satellite that rivals our own rocky planets in scale, all while orbiting another, much larger world. It is a hierarchical solar system in miniature, a planet with its own planetary scale moons under construction. This transforms our understanding of the rings from a static spectacle into a dynamic, evolving construction site, where the very laws that built our solar system are operating on a supercharged, colossal stage. But this monumental construction site operates on a timescale that feels alien to our own. The planet J1407b takes a staggering 11 Earth years to complete a single orbit around its star. One full year on this ringed giant lasts over a decade. To put that into perspective, consider the gas giants in our own neighborhood. Jupiter, the largest planet in our solar system, completes its year in just under 12 Earth years. Saturn takes about 29.5 years, so J1407b, for all its immense scale, orbits its star in a time frame not too dissimilar from Jupiter's. The crucial difference lies in the distance. J1407b orbits much farther from its star than Jupiter does from our Sun. This vast orbital distance has profound consequences for the ring system we believe surrounds it. First, it means the environment is intensely cold. Out there in the deep freeze of its wide orbit, any water ice in the rings would be frozen as hard as rock, and other volatile materials would remain locked in place. More importantly, such a distant orbit places the planet and its rings far from the disruptive gravitational tides of its parent star. In a tighter orbit, a star's gravity can pull and shear at a ring system, stripping it away or preventing it from forming in the first place. J1407b's great distance provides a quiet, stable harbor for its colossal disk to exist, a sheltered shipyard where moons can potentially form over eons without constant stellar interference. This combination of frigid temperatures and gravitational calm might be the very recipe that allows a ring system of such impossible size to temporarily hold itself together, giving us a fleeting glimpse into the violent and creative processes that build worlds. Yet for all its grandeur, this cosmic shipyard orbits a surprisingly familiar anchor. The star at the heart of this distant system, known simply as J1407, is not some exotic giant or faint dwarf. It is in many ways a mirror of our own Sun. Classified as a young, solar-type star, it shares a similar size, mass, and temperature with the star that lights our sky. But there is one profound, defining difference. While our Sun is a middle-aged star at 4.6 billion years old, J1407 is a stellar infant, a mere 16 million years into its life. To put that into perspective, if our Sun's lifetime were a 100-year human lifespan, J1407 would be a newborn just 3.5 weeks old. This extreme youth is not a minor detail. It is the single most important key to unlocking the entire mystery of the colossal rings. We are witnessing a system in its earliest, most chaotic phase of construction. At only 16 million years old, the planet J1407b and its staggering disk of debris are essentially newborns themselves. There simply has not been enough time for the physics of the system to reach a quiet, settled state. All that dark dust and rocky material has not yet had the millennia required to fully clump together under gravity and form a complete set of major moons. Nor has it had time to be fully stripped away by stellar winds or other disruptive forces. We are catching this planet in a fleeting, adolescent moment, a brief window in cosmic time where its primordial birth disk is still spectacularly visible on a scale we can detect from hundreds of light years away. It is a snapshot of our own solar system's deep past, a time when Jupiter and Saturn likely wore similar, though smaller, halos of creation. The youth of J1407 is what allows this impossible ring to exist, a temporary monument to the violent and beautiful processes that build families of worlds. This reliance on shadows means our knowledge is frustratingly incomplete. We only learn about J1407b during those rare, complex transits when it passes in front of its star. But predicting the next transit is a monumental challenge. With an orbital period of over a decade, and given the single, intricate event we observed back in 2007, astronomers cannot pinpoint exactly when it will happen again. The planet's orbit might be slightly elliptical, or other gravitational nudges could shift its schedule. We are essentially waiting for a cosmic needle in a haystack to cast a specific, jagged shadow at an unknown future date. This irregularity turns every observation into a precious, fleeting opportunity. Even when a transit does occur, the signal is not a clean, simple dip. It is a chaotic symphony of dimming and brightening caused by the complex ring structures, making it incredibly difficult to disentangle the precise properties of the planet itself from the swirling disk that surrounds it. Our most powerful telescopes today, like Hubble or even the James Webb Space Telescope, are not equipped to directly see this world. At a distance of 434 light-years, J1407b is lost in the blinding glare of its host star. It is like trying to spot a speck of dust clinging to a brilliant lighthouse lens from miles away across a foggy harbor. Direct imaging is, for now, an impossibility. So everything we understand, from the ring's scale to the potential moon, is not a photograph. It is a sophisticated inference, a detailed model painstakingly reverse-engineered from the flickering of a distant point of light. We are cosmic detectives, piecing together the scene of an event we can never directly witness, relying entirely on the subtle clues written in stolen starlight. The sheer scale of this structure forces us to confront a difficult question: how does something like this even come to be? The leading theories are as dramatic as the rings themselves, each painting a different picture of cosmic violence or creation. One compelling idea is that we are witnessing the aftermath of a truly apocalyptic collision. In the chaotic early days of this young system, a massive moon, perhaps even a planet-sized body, could have been shattered by a catastrophic impact. The resulting debris, millions of fragments ranging from dust to mountain-sized boulders, would have been thrown into orbit around J1407b. Over time, gravity would have shepherded this wreckage into a vast, flat disk, the rings we see today. This is not unlike how we believe Earth's own moon formed, from the debris of a giant impact, but here the collision was on a far grander scale, and the debris never coalesced back into a single world. Instead, it remains suspended, a glittering memorial to a planetary-scale catastrophe frozen in time. A second theory suggests a more gentle, though still immense, origin. As the planet J1407b finished forming and carved its path through the primordial cloud of gas and dust around its star, its powerful gravity could have captured and held onto an entire swath of that material. Instead of the debris coming from a shattered moon, this model proposes the rings are simply a leftover piece of the star's own birth disk, a captive ribbon of cosmic construction material that the planet claimed for itself as it grew. This would make the rings not a sign of destruction, but a trophy of formation, a belt of raw ingredients the planet pulled from the stellar nursery. Yet the most widely supported idea returns us to the concept of the circumplanetary disk. This theory posits that what we are calling rings is, in fact, the natural and expected environment of a gas giant planet in its extreme youth. When planets like Jupiter or Saturn formed, they were surrounded by their own miniature versions of a protoplanetary disk, a swirling reservoir of gas and dust from which their moons slowly assembled. In our solar system, that process finished billions of years ago, the disk material either becoming moons or falling into the planet or drifting away. At J1407b, we may simply be looking at that same process, but on a staggering scale and crucially, while it is still happening, the planet's great mass and its distant, quiet orbit allowed it to gather and retain a simply monstrous amount of this moon-forming material. The rings are the disk itself, and the gaps within them are the construction zones where future moons are being born right now. This stands in stark contrast to the leading theories for Saturn's own beautiful rings. While Saturn may have also had a large primordial disk long ago, its current rings are likely much younger and may be the recycled remains of a shattered icy moon or comet that wandered too close within the last few 100 million years. They are a relatively recent and delicate decoration, J1407b's rings, however, feel primordial. They are not a later addition. They appear to be part of the planet's fundamental architecture, a sprawling, chaotic extension of its very formation. One is a piece of jewelry added later in life. The other is the raw, beating heart of a planetary birth, still visible for us to see. This immense disk of debris faces a powerful and inevitable enemy, its own gravity. All that dust and rock, swirling in such close quarters, should naturally want to clump together. Under the relentless pull of mutual attraction, particles should collide, stick, and slowly snowball into larger bodies, eventually forming moons. It is the fundamental story of how every solid object in our solar system was built. So why hasn't J1407b's ring system already collapsed into a collection of moons? The very fact that we can see it means something is actively fighting that process, preserving this spectacular chaos. The answer likely lies in a combination of delicate cosmic forces acting as a temporary break on nature's clock. One major factor could be the planet's own powerful magnetic field. As a massive gas giant, J1407b almost certainly generates a fierce magnetic dynamo deep within its swirling interior. This magnetic field extends far out into space, and as the countless tiny, charged dust grains within the rings orbit through it, they experience a drag. This magnetic braking can subtly alter their orbits, causing collisions to be more glancing or destructive rather than gentle and sticky. Instead of merging, particles might be ground down into even finer dust, perpetuating the disk's fragmented state. Another disruptive force comes from the planet's distant but still influential star. Even from its far orbit, the gravity of the star J1407 exerts a tidal pull on the ring material. This constant stretching force can prevent the disk from settling into a calm, uniform sheet where accretion is easy. It introduces subtle vibrations and orbital resonances, regions where the push and pull of gravity create zones of instability that stir the pot, keeping the particles agitated and less likely to peacefully coalesce. And then there are the shepherds themselves. Those potential moon-sized bodies we infer from the gaps in the rings might be playing a dual role. While they are gathering mass and growing, their immense gravity doesn't just clear a path, it also herds the ring particles on either side. This shepherding action can confine the material into narrow, dense bands, but it can also pump energy into the system, like a shepherd dog constantly nipping at the heels of a flock to keep it moving. This orbital nudge can speed up particles, making their collisions more violent and disruptive rather than constructive, so we are left with a dynamic portrait of a system in a precarious balance. The natural urge to clump and form moons is being counteracted by a symphony of magnetic drag, tidal stirring, and gravitational shepherding. This suggests the rings of J1407b are not a permanent fixture. They are a transient, adolescent phase. We are likely seeing them during a narrow window in cosmic time, perhaps just a few million years after the planet formed but before its moon-forming factory completes its work. The very forces that preserve the rings today are also sealing their fate, ensuring they will eventually either be consumed by growing moons or scattered to the cosmic winds, leaving behind a more familiar-looking family of satellites. This leaves us with a profound and urgent question: is J1407b a cosmic loner, a singular freak of nature, or is it the first of a new class of worlds? Astronomers have been scouring the data for other super-ringed giants, and they have found a few intriguing candidates. One star, known as PDS 110, also exhibited a strange, complex dimming event, a deep and lengthy eclipse that hinted at a possible ring system around an orbiting companion. Yet the evidence for PDS 110 is not as clear or as detailed as the spectacular light curve from J1407. Other potential ringed exoplanets have been proposed, but none have presented a case as compelling or a structure as mind-bendingly vast as our first discovery. For now, J1407b stands alone as the most extreme and well-studied example, the king of rings in a kingdom we have only just begun to map. Its apparent rarity, however, might be a trick of perspective and time. Detecting these complex transits requires a perfect alignment of star, planet, and our telescopes. We only see the rings when they pass in front of their star, and with orbital periods spanning decades, we might simply be missing the window to observe others. Furthermore, if these colossal rings are truly a fleeting adolescent phase, then catching a planet in this brief state is like stumbling upon a single, spectacular bloom in a vast desert. The flower is not common, but the conditions that create it might be. This is where our next generation of eyes on the cosmos enters the story. The James Webb Space Telescope, with its unprecedented sensitivity to infrared light, offers a revolutionary new way to hunt for these giants. While directly imaging J1407b remains a challenge, Webb can analyze the atmosphere of stars like J1407 in exquisite detail during a transit. It could potentially detect the chemical fingerprints of the ring material itself, perhaps identifying silicate dust or other compounds as they filter the starlight. More excitingly, Webb and future giant ground-based telescopes could search for the subtle, telltale wobble in a star's light caused by the gravitational tug of an unseen, ringed planet, even when it is not transiting. We are on the verge of moving from stumbling upon these accidental giants to actively hunting for them, listening for their faint gravitational whispers across the light years. The search for more super Saturns is just beginning, and each new candidate will help us answer whether J1407b is a magnificent accident or a signpost to a whole new category of planetary architecture. This single, distant world rewrites the textbook on what a ringed planet can be. To fully appreciate its challenge, we must line it up against every example our own solar system provides. Saturn, of course, is the classic archetype, a mature and brilliant system of mostly water ice sculpted by tiny moons. Jupiter's faint, dusty rings are tenuous whispers, fed by meteoroid impacts on its inner moons. Uranus sports dark, narrow rings of charcoal-colored material, tilted dramatically on their side, while Neptune's fragmented arcs are clumpy and incomplete. Each is a unique expression of planetary environment and history, yet, when viewed through the lens of J1407b, they all share one profound commonality. They are, without exception, modest. They are delicate trimmings, decorative bands that adorn their planets without defining them. J1407b does not wear rings, it is engulfed by them. Its structure is not a trim, it is the dominant feature, a sprawling, chaotic construction zone that overshadows the planet itself. This forces a humbling realization. For centuries, we have studied Saturn's rings as the pinnacle, the gold standard of what a ring system can be. But what if our solar system's rings are not the pinnacle at all? What if they are the quiet, well-behaved end of a spectrum, and J1407b represents the wild, untamed, and colossal beginning? Our neighborhood may showcase the peaceful retirement of ring systems, while the wider galaxy is filled with the violent construction sites of youth. Astronomers are now compelled to reconsider the very upper limits of size and complexity. The rules we derived from Saturn about stability, composition, and scale simply do not apply here. A ring system can be 200 times larger. It can be dark and dusty, not bright and icy. It can contain forming moons larger than Mars. This single point of flickering light proves that the processes we thought we understood have a far greater and far more spectacular range than we ever dreamed. It suggests that our own solar system, with its orderly orbits and relatively delicate rings, might be the exception rather than the rule. We may live in a quiet suburb of the galaxy, while the real cosmic drama of planet and moon formation unfolds in these colossal, chaotic disks around distant, young giants. This transforms the rings from a spectacle into a cosmic assembly line. The sheer volume of material contained within that dark, sprawling disk is almost beyond comprehension. If we could gather every speck of dust, every boulder, and every chunk of rock from the rings of J1407b and compress it together, we would have enough raw planetary building blocks to construct multiple worlds on the scale of our own. Conservative estimates suggest the total mass locked in that disk is at least the mass of our entire Earth. More daring calculations, based on the depth and complexity of the shadows cast, propose it could be many times that, perhaps even equivalent to the mass of several Earths combined. Think about that for a moment. All the material that makes up our blue marble, with its vast oceans, towering mountains, and deep iron core, is just the baseline. There could be enough stuff in that one ring system to build 3, 4, or even 5 whole new Earths. But here, the process isn't creating a single, lonely terrestrial planet. Instead, that immense reservoir of mass is the feedstock for an entire lunar production line operating around a gas giant. We are likely seeing the direct parallel to the process that, 4.5 billion years ago, built the most iconic moons in our own solar system. Around young Jupiter, a similar circumplanetary disk of gas and dust once swirled. Within it, through countless collisions and gravitational gatherings, the Galilean moons were born: Io, Europa, Ganymede, and Callisto. Around Saturn, the same process crafted Titan, a world with a thick atmosphere and methane lakes, a moon larger than the planet Mercury. The rings of J1407b are not a decorative feature. They are the factory floor where such moons are manufactured. The dense bands we infer from the starlight are like conveyor belts of concentrated material. The gaps are the clean workstations, cleared out by the gravitational influence of the growing moons themselves. That one vast gap, potentially shepherded by a protomoon the size of Mars, is a stunning piece of evidence. It shows the factory is already in operation, with the first major products taking shape and literally clearing their own orbital path. We are not looking at a static picture. We are watching a time-lapse of solar system formation, sped up to a cosmic scale, where the raw ingredients for entire worlds are being sorted, gathered, and assembled before our very eyes. The experience of time on a moon within this system would be utterly alien. Orbiting a planet whose year lasts over a decade, a satellite would find its own existence governed by 2 immense celestial clocks. The first is the slow, ponderous march of the planet around its star, marking seasons that stretch for Earth years. The second, and far more dramatic, would be the daily rhythm imposed by the colossal rings themselves. For any moon orbiting close to the planet, inside the inner edge of that vast disk, the sky would be dominated by an impossible wall of darkness. The rings would not appear as a delicate line, but as a ragged, mountainous arc that blots out half the universe, stretching from one horizon to the other. Sunlight would only reach the moon's surface in narrow windows, when it passed above or below the plane of the rings, but for a moon orbiting within the rings or nestled in one of the gaps, the experience would be a spectacle of shadows on a scale we can barely conceive. The rings would not be static. Their tilt relative to the planet's orbit around the sun would create profound seasonal shifts. For years at a time, the rings could cast their shadow directly onto the planet's northern hemisphere, plunging it into a deep, prolonged twilight. Any inner moons caught in that shadow would experience a season of perpetual dusk, a global cooling that could last for Earth decades. Then, as the planet continues its slow journey, the shadow would migrate across the equator and into the southern hemisphere, reversing the effect. The climate on any potentially habitable moon would be at the mercy of this celestial cycle. Imagine a world where winter is not a matter of months, but a global dimming that lasts for a generation, where temperatures plummet as the primary source of light is slowly eclipsed by a billion-mile-wide barrier of rock and dust. The day-to-day experience would be even more striking. From the surface of a moon like the one potentially shepherding that vast gap, the rings would arch across the sky as a textured, dusty tapestry. But they would be a tapestry in motion, As the moon orbits, the geometry between it, the rings, and the sun would constantly change. There would be times, perhaps for months on end, when the moon is perfectly aligned so that the rings eclipse the sun entirely. This would not be a brief afternoon shadow. This could be a permanent solar eclipse lasting for weeks or months, turning day into an eerie, star-filled night, with only the faint, filtered glow from the planet's cloud tops providing any illumination. Then, as the orbit continues, the sun would reappear, first as a sliver peeking over the ring's edge, then flooding the landscape with sudden, unfiltered light for an equally long summer. The light itself would be strange and sculpted. During the long eclipses, the only light might be a dim, reddish glow reflected from the immense planet's atmosphere, or the pale shimmer of starlight scattered by the ring's countless dust particles. When the sun was visible, it would often be sliced into brilliant bands and crescents by the dense lanes of ring material, creating complex patterns of light and dark that would crawl across the terrain with the moon's rotation. The very concept of a sunrise would be rewritten. Instead of a clean arc over a flat horizon, the sun might emerge from behind a towering cliff of cosmic debris, its light fractured into 100 beams through 1,000 gaps. The sky here is not an empty dome, but a structured, dynamic architecture that directly dictates the rhythm of life, light, and temperature on a scale that makes our own planetary seasons seem like the gentle ticking of a second hand. Within that swirling disk of dark rock and potential moons, there is a hidden actor, an almost invisible component that holds enormous power over what we see. This is the fine dust, the microscopic powder generated by the constant, low-grade violence within the rings themselves. While we picture the rings as containing boulders and mountain-sized chunks, a significant portion of their mass is likely in the form of particles finer than sand, grains smaller than the width of a human hair. This dust does not sit idly by. The rings are a shooting gallery, micrometeoroids, tiny specks of rock traveling at incredible speeds from the depths of interstellar space, constantly pepper the disk. When one of these high-velocity projectiles strikes a larger ring particle, it doesn't just chip it, it vaporizes a tiny portion of the surface in a miniature explosion. This process, called impact vaporization, blasts a fresh cloud of even finer dust into the surrounding space. Each impact is a tiny fountain of new powder, a perpetual regeneration system for the dusty component of the rings. But the drama doesn't stop there. This freshly created dust is electrically charged by the harsh ultraviolet light from the star J1407. Once charged, these particles become slaves to the planet's powerful magnetic field. They no longer move solely under gravity's pull. They get caught in magnetic field lines, spiraling along invisible tracks that can lift them up out of the main ring plane. This creates tenuous, dusty halos and faint vertical structures extending above and below the otherwise flat disk. Imagine a busy, flat highway of boulders and ice, but with a constant, shimmering mist rising from its surface, a mist that dances to the tune of an invisible magnetic force. This intricate dust dynamics adds a maddening layer of complexity to the starlight signal we try to decode. When the planet and its rings transit the star, the large, solid blocks of material create sharp, clean dips in brightness. But the fine dust scatters the starlight. It doesn't just block it, it diffuses it, bending and redirecting photons around the edges of particles. This scattering effect softens the shadows. It can make the edges of a transit signal appear fuzzy or graded, and it can create a subtle, lingering dimming even before and after the main body of the rings has fully passed in front of the star. It's the difference between the sharp, black shadow of your hand and the soft, hazy penumbra around it when you hold it up to a bright light. For astronomers trying to reverse engineer the exact structure of the rings from that single, wobbly light curve, the dust is a confounding factor. It acts like a cosmic fog, blurring the crisp edges of the data and forcing scientists to model not just the arrangement of large objects, but the behavior of countless trillions of tiny, magnetically influenced specks. This means the grand architecture we infer, The gaps and bands is actually filtered through this pervasive, scattering haze, making our map of that distant system a best interpretation of a profoundly complex and dynamic reality. This invisible magnetic architecture could paint the rings with light. A gas giant as massive as J1407b almost certainly generates a ferocious magnetic field deep within its churning interior. This magnetosphere, a vast bubble of invisible magnetic force extending millions of kilometers into space, would completely engulf the inner regions of the colossal ring system. Within that dark disk, countless dust grains, constantly sandblasted by starlight and micrometeoroid impacts, become electrically charged. These charged particles are no longer just passive rocks following gravity's rules. They become trapped, forced to spiral along the planet's powerful magnetic field lines like beads on an invisible wire. This interaction would channel immense rivers of charged particles, not just from the solar wind, but from the rings themselves, pouring down toward the planet's magnetic poles. The result would be auroras on a scale that redefines the word. On Earth, our northern lights are a delicate, shimmering curtain caused by solar particles interacting with our upper atmosphere. At Jupiter, the auroras are immense, permanent rings of ultraviolet light fueled by particles from its volcanic moon Io, but at J1407b, the auroral engine would be fed by its own rings. Imagine the entire inner edge of that 100 million kilometer disk acting as a particle accelerator, funneling a constant, unimaginable torrent of charged dust into the planet's polar regions. The light show would not be confined to the planet's atmosphere. Auroras could ignite within the ring material itself. As these high-energy particles slam back into the dust and ice of the inner rings, they would cause the very particles to fluoresce, to glow with their own eerie light. The entire inner ring system could become a faint, luminous halo, a self-illuminating structure visible from its own moons. The scale is almost impossible to visualize. An auroral display at J1407b wouldn't just be bigger than Earth's, it could be larger than the entire orbit of Jupiter, a swirling, dynamic storm of light woven directly into the fabric of the rings. This transforms the rings from a passive, shadow-casting structure into an active, glowing component of the planet's electrical system, a cosmic neon sign powered by the relentless grinding of dust and the silent pull of magnetic force. The true revolution in understanding this colossal ringed world is just over the horizon. Our next generation of telescopes, instruments of unprecedented power, are preparing to turn their gaze toward stars like J1407, not to wait for a single, unpredictable transit, but to hunt for the subtle whispers these giants leave behind. The James Webb Space Telescope, already rewriting the rules of infrared astronomy, holds a key tool for this search, while directly imaging J1407b remains a monumental challenge. Webb can perform a kind of celestial chemistry experiment. During a future transit, its powerful spectrographs could analyze the starlight filtered through the rings themselves. Each chemical element and compound in that vast disk absorbs light at very specific colors, or wavelengths. By dissecting that filtered starlight into its constituent colors, Webb could identify the unique fingerprints of silicate dust, carbon compounds, or even water ice hidden within the dark material. This would finally answer the fundamental question of what these rings are made of, moving us from educated guesses to hard chemical data. Is it the gritty dust of shattered rock, or does it hold the frozen seeds of future icy moons? Webb's spectral analysis could tell us, on the ground a new behemoth is rising. The extremely large telescope, or ELT, being built in the Chilean desert, will gather more light than any optical telescope ever constructed, with a primary mirror spanning an astonishing 39 meters. Its sheer light-gathering power, combined with advanced adaptive optics to cancel out the blurring of Earth's atmosphere, will allow it to perform a different kind of magic. The ELT might be able to detect the faint, reflected glow of the rings themselves, separating that light from the overwhelming glare of the parent star. This would give us our first potential image, not a detailed photograph, but a data point confirming the ring's albedo or reflectivity, and perhaps even hinting at its structure. More importantly, the ELT's incredible precision could measure the star's subtle wobble with unmatched accuracy. As the massive planet J1407b orbits, its gravity tugs the star back and forth in a tiny, rhythmic dance. By tracking this wobble over time, astronomers could pin down the planet's exact mass and orbital characteristics with far greater certainty, finally resolving whether it is a superjupiter or a brown dwarf. This gravitational census will be crucial for finding other ringed giants, even those whose orbits never line up for a transit, by detecting their gentle pull on their host stars. Joining this effort will be the Nancy Grace Roman Space Telescope, slated for launch later this decade. Roman's wide field camera is designed to perform vast, continuous surveys of the sky, monitoring millions of stars for changes in brightness. This makes it the perfect instrument for catching the next complex transit event, not by luck, but by relentless, systematic observation. Where we observed J1407's dimming for weeks, Roman could monitor it and thousands of stars like it for years. It could catch the beginning, middle, and end of a full transit, providing a complete, uninterrupted light curve of breathtaking detail. This data would be like going from a rough sketch of the rings to a high-resolution topographic map. Every dip, every plateau, every subtle flicker would be recorded, allowing astronomers to model the ring's structure with incredible precision, the exact widths of gaps, the density of bands, and the potential orbits of multiple forming moons within the chaos. Together, this trio of observatories represents a new era. We are moving from stumbling upon a single, magnificent accident to conducting a deliberate, multi-pronged investigation of a new class of celestial architecture. The answers are written in the light, and for the first time, we are building the tools to read every word. Amidst this cosmic construction site, a tantalizing question arises. Could any of the moons being forged within those colossal rings ever become a home for life? It is a profound what-if scenario, one that pushes the boundaries of our search for habitable worlds far beyond the familiar orbits of stars. The challenges are, to put it mildly, monumental. First, consider the light or the lack of it. The parent star, J1407, is a sun-like twin, but the planet orbits at a vast, frigid distance. Any moon would receive only a feeble trickle of warmth and light, a tiny fraction of what Earth enjoys. Surface temperatures would be bitterly cold, likely plunging hundreds of degrees below zero. Then there is the planet itself. A gas giant of such immense mass almost certainly generates a ferocious radiation belt, a storm of high-energy particles trapped by its powerful magnetic field. A moon orbiting within that hostile zone would have its surface constantly sterilized, its atmosphere stripped away by this relentless barrage, but the universe often finds a way to balance its extremes. One potential source of energy could come from within. If a moon's orbit is slightly elliptical, the relentless gravitational tug of war with the massive planet would flex and squeeze its interior. This process, called tidal heating, generates internal warmth through friction. In our own solar system, this is what drives the spectacular volcanic eruptions on Jupiter's moon Io and keeps the global subsurface ocean liquid on Europa. For a large moon around J1407b, this internal furnace could provide crucial heat, potentially maintaining a liquid water ocean beneath a thick, protective shell of ice. Such a moon would be a dark, frozen world on the surface, but a warm, watery haven below. The final critical ingredient is atmosphere. For life as we know it to have any chance on the surface, a moon would need a very thick, insulating atmosphere, rich in greenhouse gases like methane or carbon dioxide. This gaseous blanket could trap what little stellar heat arrives and, more importantly, retain the internal heat from tidal forces, creating a surface temperature that might allow for liquid water. Titan, Saturn's largest moon, provides a perfect analogy. It is far from the sun and bitterly cold, yet it possesses a dense, hazy atmosphere thicker than Earth's. While its surface rivers and lakes are of liquid methane, not water, it proves that moons in the outer solar system can retain substantial atmospheres. A large, massive moon forming in the J1407b system, one with sufficient gravity and volcanic outgassing from tidal heating, could potentially develop a similar shroud. So, while the odds are long and the environment is harsh beyond imagination, the recipe is not entirely absent. It would require a perfect and fragile alignment, a moon large enough to hold a dense atmosphere, with an orbit that provides just the right amount of tidal heating, positioned carefully to avoid the worst of the radiation belts. We are likely looking at a system where the most habitable real estate would not be a planet, but a distant, dark moon, warmed from within and shrouded in an alien sky, a hidden oasis orbiting a ringed Titan in the perpetual twilight of deep space. Such a staggering claim demands rigorous skepticism. Could the bizarre dimming of star J1407 be explained by something other than a super-ringed planet? The scientific community explored every alternative, as good detectives should. One early hypothesis proposed a massive swarm of comets, a cloud of icy debris passing in front of the star. While cometary swarms can cause irregular dimming, the event at J1407 was far too symmetrical and structured. A random cloud of comets would not produce the clean, repeating patterns and sharp gaps seen in the data. Its signal would be far more chaotic and brief. Another idea suggested the planet itself might be profoundly distorted, perhaps an egg-shaped world due to extreme rotation, yet even the most oblate spheroid could not account for the weeks-long, multi-staged eclipse with its intricate plateaus and dips. The shadows were simply too complex to be cast by a single solid object, no matter its shape. Instrumental error was also carefully ruled out. The dimming was observed independently, and the light curves features were far too specific and repeatable across different data sets to be a glitch. After methodically eliminating these other possibilities, the ring model emerged not as a wild guess, but as the only explanation that fit every detail of the evidence. It provided a natural mechanism for the long duration, the complex substructure, and the presence of clean gaps. The model made a bold prediction, too. It suggested that if this was a young system with a vast disk, the star itself might show signs of youth. Subsequent observations confirmed that very prediction, measuring star J1407's rapid rotation and high magnetic activity, classic hallmarks of a stellar teenager. This independent confirmation strengthened the ring hypothesis tremendously, yet mysteries stubbornly persist. The exact mass of the central object remains frustratingly uncertain, leaving us unsure if it is a planet or a brown dwarf. We have only witnessed one full transit event, leaving the ring system's long-term stability and true composition open for debate, and the biggest question of all lingers in the darkness between transits: what is happening in that system right now, 434 years ago? The rings may have already collapsed into moons or been stripped away, transforming entirely. We are left with a single, magnificent snapshot of a cosmic moment, a puzzle solved enough to awe us, but with edges still blurry enough to humble us. That single point of flickering light does more than just defy our textbooks. It changes our place in the cosmic story. For scientists, J1407b is a direct and exhilarating challenge. Our models of how planets and moons form were built from the evidence of our own solar system, a single data point in a galaxy of hundreds of billions of stars. This discovery is a second data point, and it is an extreme outlier that forces us to ask if our models are incomplete, or if our own neighborhood is unusually quiet. It proves that the processes of accretion and disk dynamics can operate on a scale we never anticipated. that a planet can hold onto a moon-forming disk of such staggering mass. Every equation about ring stability, tidal forces, and orbital resonances must now be tested against this colossal benchmark. It turns planetary science from a study of familiar archetypes into a detective story where the most important clues come from the exceptions, from the freaks that show us just how wide nature's brush can paint. For the public, its impact is more visceral. We grew up with Saturn as the iconic ringed world, its image a symbol of celestial beauty and order. J1407b shatters that symbol. It replaces a delicate, familiar halo with a monstrous, shadowy disk that feels more like a structure from epic science fiction. This matters because it makes the universe feel alive with possibility again. It is a tangible piece of evidence that the cosmos is not just a slightly varied copy of our solar system. There are architectures out there that dwarf our imagination, realities so extreme they seem to bend the rules. This discovery moves planets from being mere points of light in a telescope to being characters in a grand, ongoing narrative of construction and chaos. It tells us that the galaxy is not only stranger than we suppose, but stranger than we can suppose, and that we have only just begun to read its first few pages. Ultimately, J1407b serves as a profound reminder of cosmic humility and wonder. It exists 434 light-years away, meaning the shadow we observed in 2007 was cast before Shakespeare wrote his first play. We are studying a fossil of a young system's adolescence, a moment frozen in time that may have already transformed into something else entirely. Yet, by decoding its faint signal, we connect our curiosity across that immense gulf. We are reminded that exploration is not just about visiting new places, but about seeing with new eyes. This ringed giant challenges us to let go of our solar system-centric view and embrace a universe of magnificent, overwhelming diversity, where the only true limit is the scope of our questions. These scientific revelations demand a visual language to match their scale. Without a direct photograph to guide us, a vibrant collaboration has emerged between astronomers and artists, transforming data points and light curves into breathtaking cosmic vistas. The visualizations of J1407b are not mere guesses. They are informed translations, taking the dry numbers of orbital mechanics and ring density and rendering them into something the human mind can truly feel. The most common and powerful depiction shows a dark, majestic gas giant, its cloud bands deep burgundy or charcoal gray under the faint light of its distant sun. But the planet itself is almost an afterthought, utterly dominated by the structure that engulfs it. From the viewer's perspective, the rings are seen nearly edge-on, a razor-thin line of absolute blackness that slices across the face of the planet and stretches to infinity in both directions. This thin line is the key artistic choice that conveys the impossible scale. It emphasizes the rings are not a fluffy halo, but a flat, sharp plane of incredible precision, a blade of darkness cutting the starfield in two. The rings are often shown not as bright ice, but as a deep, stratified brown and gray, layered with countless fine dust lanes, capturing the scientific consensus of a dusty, rocky composition. In the background, the young star J1407 shines with a slightly cooler, more orange hue than our Sun, a reminder of the system's tender age. Some visualizations take us to the surface of a hypothetical moon within the gap, looking up at a sky where that thin black line arcs from horizon to horizon, backlit by the star to reveal a translucent, granular structure, like looking through a billion-mile-wide sheet of smoked glass. These artistic interpretations do more than decorate a science article. They perform a crucial cognitive function. They give form to the abstract, allowing us to emotionally connect with a discovery that is, at its core, a series of mathematical inferences. They help us internalize the sheer dominance of the rings over the planet, the profound tilt of the system, and the eerie, filtered quality of light that would permeate this realm. By painting the shadow we detected, artists complete the loop of discovery, turning data back into a world we can, in some way, visit in our minds. They remind us that the universe's beauty is not reserved only for what we can directly see, but also for what we can, through science and imagination, faithfully reconstruct. The anticipated moment arrived in the spring of 2017. Based on the singular, complex transit observed a decade prior, astronomers around the world had calculated when J1407b should once again pass in front of its star. Telescopes were pointed, observation time was scheduled, and the scientific community held its collective breath, ready to capture a second, even more detailed portrait of the super rings. The predicted date came and went. The star's light remained steady, unwavering. There was no grand eclipse, no intricate shadow play, no confirmation of the colossal architecture. The ringed giant had, from our perspective, simply vanished. This non-event was, in its own way, a monumental discovery. It told us that our simple extrapolation of its 11-year orbit was wrong. The planet's path is not a perfect, predictable circle, but likely a more elongated ellipse. A slight eccentricity in its orbit would mean its transits do not occur like clockwork. They can arrive early or late by months or even years depending on our viewing angle. Our map, drawn from a single data point, was incomplete, but the silence from J1407 held another, more thrilling possibility. What if the rings themselves are gone? The sheer scale of that disk always suggested it was a transient, adolescent feature. In the decade between our observations, the delicate balance of forces preserving it may have finally tipped. The relentless pull of gravity could have won, causing the vast reservoir of dust and rock to finally coalesce into full-fledged moons, draining the ring system of its raw material. Or perhaps the growing protomoons themselves, through their gravitational shepherding, scattered the remaining debris, sending it spiraling into the planet or drifting off into space. The rings of J1407b may have been a spectacular but fleeting phase in this system's life, a burst of cosmic construction that we were extraordinarily lucky to witness just once. This unexpected twist transforms the mystery from a static puzzle into a dynamic story. We are no longer studying a fixed monument, but a living, evolving system caught in the act of profound change. The very fact that it defied our prediction is the clearest signal yet that we are dealing with something raw and real, a chapter of planetary evolution unfolding in real cosmic time. The giant is not lost, it is merely waiting, its next move hidden in the darkness, challenging us to keep watching. That single, fleeting glimpse of a disappearing ring system rewrites the foundational story of our own home. The colossal rings of J1407b are not just a curiosity, they are a time capsule, a direct window into the violent nursery where gas giants and their families of moons are born. This discovery fundamentally reshapes the theory of planet formation by demonstrating one critical truth: massive, long-lived circumplanetary disks are not just possible, they can be the dominant feature of a young planetary system. For decades, our model was built on the quiet, finished product we see around Jupiter and Saturn. We inferred that they must have once had disks, but those disks were thought to be relatively short-lived, perhaps dissipating within a few million years as moons quickly coalesced. J1407b screams that this timeline is not universal. Here, a disk of staggering mass has persisted, visible and dynamic, around a planet that is already 16 million years old. This tells theorists that the process of moon formation can be a slow, messy, and spectacularly drawn-out affair. The reservoir of raw material available is far greater than we assumed, meaning the potential for building moons is correspondingly vast. It suggests that the Galilean moons of Jupiter or the large moons of Saturn might not have formed from a modest, quickly exhausted supply. Instead, their parent planets may have also possessed these colossal, enduring disks, acting as rich factories that methodically built worlds over many millions of years. Our solar system's giants simply finished their construction and cleaned up the site long ago, leaving us with only the final products and no memory of the monumental scaffolding that once surrounded them. J1407b is that scaffolding still in place, proving that the architecture of creation can be as immense and complex as the worlds it builds. The ultimate fate of those impossible rings hangs in the balance between two cosmic forces. On one side is the relentless pull of gravity, the universe's great architect, constantly urging the countless particles to come together, to clump and merge and build. On the other side are the agents of chaos, tidal stresses, magnetic drag, and the gentle but persistent pressure of starlight itself, all working to grind the material down and blow it apart. Which force will win dictates whether this system becomes a crowded family of worlds or a lonely, stripped giant. The timescales involved are almost beyond human comprehension, measured in millions, not thousands of years. This is not a story with an ending we will ever witness, but by understanding the physics, we can project its final chapter. The most majestic outcome would see gravity emerge victorious. Over the coming millions of years, the densest bands within that dark disk would become nurseries. Within them, through countless gentle collisions, dust grains would stick together, forming pebbles, then boulders, then mountain-sized planetesimals. As these growing bodies plowed through the disk, their gravity would clear wider paths, sweeping up material and accelerating their own growth. The gaps we infer from the starlight would be the birthplace of these new worlds. That one vast gap, potentially shepherded by a Mars-sized protomoon, is a preview of this process already in motion. If it continues, that single object could become the cornerstone of an entire lunar system, a Titan or Ganymede-scale world. Other gaps would spawn their own moons, creating a hierarchy of satellites, perhaps dozens of them, ranging from small, captured asteroids to major planetary bodies. The end state a billion years from now could be a gas giant orbited by a full retinue of large, complex moons, a miniature solar system with its own geology, atmospheres, and perhaps even subsurface oceans. The colossal rings would be gone, consumed in the act of creation, their material now locked into solid, permanent worlds. Yet the alternative is just as plausible, and perhaps more likely given the system's frenetic energy. The very forces that currently preserve the rings may ultimately destroy them. The constant bombardment by micrometeoroids doesn't just create dust, it slowly pulverizes the larger particles, grinding them into ever finer powder. Starlight, while faint at this distance, exerts a tiny but relentless pressure on this fine dust. Over millennia, this radiation pressure can push the smallest particles out of the system entirely, or spiral them slowly inward toward the planet. Meanwhile, the gravitational tides from the star, though weak, continually stretch and perturb the disk, preventing it from settling into a calm state where accretion can easily occur. The planet's own fierce radiation belts could also blast the inner regions of the rings, eroding them away molecule by molecule. In this scenario, the rings do not coalesce, they simply dissipate. They fade like a cosmic sandcastle in a slow-motion wind. The material either falls into the planet's atmosphere in a perpetual, silent rain of dust, or it is ejected into the darkness of interstellar space. The end state here is a solitary gas giant, perhaps with a few small, captured moons from elsewhere, but no grand family born of the rings. The majestic disk would vanish, leaving behind only a faint, dusty memory and a profound question for any future observers: what spectacular structure once stood here? The deciding factor may be the sheer mass of the disk itself. There is a critical threshold in these cosmic equations. If the ring system contains enough material, its own collective gravity can overcome the disruptive forces, locally collapsing to form moonlets even amidst the chaos. If the disk is below that threshold, it remains just a disk, destined to be scattered and lost. Current estimates suggest J1407b's rings sit right on that razor's edge. They may have just enough mass to eventually form a few major moons, but not enough to completely resist erosion. The most likely future, then, is a hybrid one. A handful of the largest protomoons, like the one in the vast gap, will successfully form, sweeping up the material in their immediate vicinity, but the majority of the finer dust and smaller debris in the outer, more tenuous regions of the rings will be stripped away by stellar winds and radiation pressure. The system would end not with a crowd of moons, but with a few dominant survivors, orbiting a planet circled by only the faintest, most ephemeral haze, a ghost of the colossal structure that once was. This transformative process, whether it leads to moons or dust, will define the character of this distant system for the rest of its existence, turning a fleeting spectacle of youth into the permanent architecture of maturity. That flickering of a distant star, a single anomaly in a sea of data, has led us on an incredible journey. We began with a jagged, unexplainable dip in starlight, a puzzle written in shadow. Through the patient work of astronomers, that shadow transformed into a map, revealing a world that defies all our familiar scales. We have traveled to a planet, J1407b, whose rings are not merely larger, but 200 times more vast than the entire glorious system of Saturn. We have explored a place where rings are not delicate adornments, but a sprawling, dark construction zone, a factory floor where moons the size of Mars may be taking shape within clean, gravitationally carved gaps. And we are left, ultimately, with more questions than answers. What is the true nature of the central object? Have the rings already vanished, giving birth to new worlds? We may never know for certain, yet that is the true gift of this discovery. It is a powerful reminder that the universe is not a museum of static exhibits, but a dynamic, evolving arena of endless creativity. For every rule we think we understand, there is a distant point of light waiting to rewrite it. The cosmos is filled with architectures of such staggering scale and beauty that they humble our imagination. So what does this super Saturn make you wonder? Does it spark curiosity about what other impossible structures might be waiting in the dark? Share your thoughts below, and let's keep looking up together.